For our second lesson in beam deflections, we're going to learn how to draw consistent qualitative deflected shapes. We'll talk about boundary conditions and continuity conditions, and we'll also have more practice at determining the deflection of a beam along its length, finding maximum deflections, and those sorts of things. There are going to be, for beam structures, 3 important keys as we anticipate what the deflected shape of the structure is going to be. They're all important. The moment curvature is one of the first ones you ought to think about, that when we have positive bending moment we have smiley face type of curvature, and when we have negative moment we have hogging or frowny face in the overall deflected shape. Boundary conditions means, well, what happens at the supports? So the 2 most common kinds of conditions are the pin or the roller kind of support, which does not have any resistance to rotation, so the deflected shape, no matter where it goes, whether we end up with clockwise rotation as shown here or counterclockwise as the dotted line, that beam started off as horizontal and then that beam end rotates a little bit. Whereas the fixed end is going to have absolutely no translations and no rotations either. So the deflected shape, whether it's frowny face negative moment as I got shown here, or the dotted line being the positive bending moment, when it comes in right at that support it should have absolutely zero slope, no change at all in what happens at that location. So that's just 2 examples of boundary conditions. And then the third very important thing are the special conditions, which are also related to continuity situations. So for instance, if we had a beam that had a pin and a roller support and also internal hinge, then we'd have to deal with, when I showed a little load here, and maybe then we get this little upwards nice pretty smiley face portion right through this little middle portion, and then that's going to cause that hinge to rise up. Well, that's the continuity there, that little piece on the left side of the hinge, a little piece on the right side of the hinge. Well, they've got to have the same displacement, but the rotation of that, the tangents of those 2 pieces are going to get broken. That's what the hinge allows. Initially those were exactly the same slope on either side of the hinge, and when the hinge moves, then that's allowed to rotate in a discrete amount right at that specific location. So we have a situation where we break the slope, but we have continuity in the transverse displacement right at that hinge. Those are our 3 keys for drawing consistent qualitative deflected shapes.